Okay, welcome to two-level models for complex survey data. We're now going to look at survey weights, which is another kind of defining feature of PISA data and other large-scale education assessments. The reason for these weights is, of course, because we don't have a simple random sample of schools. Within schools, we don't necessarily have a simple random sample of students. And so the data that we have are not representative of the population, yet the population is the very thing we want to describe. So you need to use the weights which are provided to re-weight your sample analysis so that it is representative of the population. We will look at how to do this. We'll look at some of the things not to do, and we'll discuss some of the kind of scaling issues along the way. Okay. Very interesting. It's quite complex, and probably the most complex of the four lectures. We're going to use the same PISA data. Okay, so again, UK, again, the 13,000 students within 470 schools. We're not going to worry about plausible values. Okay, let's switch that off for now and analyze just plausible value 1. Okay, these are building blocks for any final analysis. You would combine what we did in the previous lecture with this. Along the way, we'll talk about the nature of the two-stage sampling, the nature of stratification, unequal sampling probabilities, oversampling of particular groups. We'll talk about these issues. We'll talk about the sampling probabilities and the weights provided by PISA, and we'll note that there's some non-response adjustments to make things more complex. And then we'll see that from the data at hand, we can obviously describe the number of students in schools, which I've already told you. But we can also talk about other concepts like the effective sample size. And even from the weights provided, we can get back to the actual implied population number of schools. How many schools are there in the population of the UK? How many students are there in the population? How many students per school are there in reality? We can get that from the weights. We'll look at kind of a correct application of survey weights, but note that we have to think carefully about scaling. Okay. And we'll look at some ways which are definitely wrong as well. But ultimately, there isn't an agreed on best practice. And so you're going to have to do a sensitivity analysis, different scaling. And in those kind of sensitivity analysis, we always hope that it doesn't make a difference, right? And that we hope that we can argue the numbers move around a bit, but not substantially so. My conclusions don't change. Everything's okay. It's a robustness check. Okay. Now, when things do change, and your results really hang off which scaling version of the weights you use, then you suddenly have to go and have to think more deeply as to what's appropriate. When you get similar results from these different methods, you don't have to think so deeply. Okay. Yeah. So, right. So, So in general, with survey data, in education with students within schools, often what will happen is that we do have a list of all schools in the population, and from that, which is the sampling frame, and from that we'll take a sample. Okay, but often it's not a random sample. Often we might oversample particular schools which are rare, for example. So in England, I was in England, if I was doing a sample of schools, I would oversample grammar schools. We have 3,000 secondary schools. I've only got 160 grammar schools, but wow, everyone will always ask, what about the grammar schools? Yeah, so if I take a 5% sample of schools, I'll end up with, 150 schools. On average, 5 are grammar schools. It's not enough to say anything about grammar schools. And so I'd oversample grammar schools and therefore undersample non-grammar schools. Okay, so that would be a good example. Also, you might be interested, for example, in ethnicity, say, and some ethnic groups, which might be of concern to research, are very rare. Let's say gypsies or traveller communities. So in the ONS ethnicity classifications, we have that as one of the 20 groups, but they're rare for the population as a whole. So if I wanted to say something about them from the data, I'd have to oversample them. Otherwise, it just wouldn't be enough to get reasonable precision. So those are the motivations for why we're not doing a simple random sample of schools. Within each school, a simple random sample of students. We wouldn't have enough grammar schools. We wouldn't have enough rare ethnic minorities. But of course, if all the researcher wants to do is subgroup reporting, what are the results of grammar schools? What are the results of non-grammar schools? That's fine. they can use the data really as is. But if they also want to do some aggregate analysis saying, well, what's happening in the UK as a whole, you've now got a very distorted sample. You've oversampled grammar schools, which are high achieving, undersampled everyone else who are lower achieving, the overall mean score is too high. And that's when you need the weights, okay? And so survey weights would be collected, would be generated and provided with the data. And as long as we use those in the analysis, we can recover an unbiased estimate of what the UK-wide average score is, despite having an unrepresentative sample. So we know how it's unrepresentative, and we built it in. Okay. So if you don't use the weights, the risk is you may get biased parameter estimates. So let's talk about PISA. So, and we're going to look at student maths achievement again, and it's a two-stage stratified sample. So the most important thing with UK data is that they've oversampled Scotland, Wales, and Northern Ireland, and therefore undersampled England. Okay, because you want to do some subgroup reporting by each country, and in particular, they've oversampled Wales and Northern Ireland because they're smaller than Scotland. So that's crucial. And so if you're saying, well, what's the UK average score? Well, if it differs between the 4 countries, you're going to get it wrong unless you use the weights. Not only that, that's the most important stratification which has happened. But there are also, within those countries, further stratification by region, by school type, and so on. And it's done slightly differently, as far as I could understand, in the 4 countries. Broadly similar, but with some slight differences. But in PISA, within each school, students are sampled at random. Okay. There isn't any kind of systematic oversampling, as far as I'm aware, of particular ethnic groups. And in some PISA countries, every PISA country does it differently. So if you go to France, it'll be different again. And in some countries, they will oversample and so on. But my understanding in the UK is that there isn't. What they went for was 40 students per school. And of course, if it's a small school, and there's 27 pupils with a max of 27, but we try to get 40. Okay, so there is this kind of stratification at level 2, unequal sampling probabilities at level 2, oversampling of Wales, Northern Ireland, and Scotland. But within any sampled schools, they just took, in theory, they took 40 at random. But of course, just because you told a school, well done, you're in the PISA sample, the school might be like, oh, I don't want to do that. Okay, so obviously you've got non-response from schools, in which case they try and substitute in a similar school in terms of its characteristics. They've got a list of similar schools ready. Okay, and where they're not able to do that, okay, you then need to upweight any schools that were sampled and similar. Okay, because they weren't able to find a replacement. So yeah. So that happens. Scheduled?
Okay. Good.
And then at the student levels, there is some non-response adjustments, I believe, by gender and which year group you're in, but it's kind of pretty limited. So again, there's like loads of complexity going on. Okay, you start off with these weights, which are reflecting unequal sampling probabilities, but ultimately they get adjusted for missing data as well. It's fascinating reading it all. Okay, so this is what it would look like. If you open up the data in PISA, well, first of all, what I did was you get a school level data set and a student level data set, and you need to merge the two. Okay, so you merge the school variables into the student level. That's what I did. So here I'm looking at, it's the same kids as before, but I'm only looking at plausible value 1, students within schools, the gender dummy variable. I've now got a variable region because, of course, we know that's the most important stratified school characteristic. And then we've got these 2 variables here. Okay, we've got a kind of something which is a level 2, but we've got a school weight and something which is an overall student weight. We've got these weird and wonderful high numbers. You just look at that and go, what do I do with that? Okay, and then you go, you try and look up PISA documentation. What do I do with it? And it's not easy to follow. Like you just want someone to say, do this. Here are the 5 commands in Stata. Just do that. And yeah, this is quite a complex thing.
So yeah, we're only going to look at plausible value 1, but in reality, what you do in this lecture, you combine with what we did previously. Okay, so let's just go back to basics a little bit. So there are 3 types of probabilities we could consider. We've got P subscript J. Okay, so from the finite population of all, whatever it is, 4,500 secondary schools in the UK, okay, that's our sampling frame. We are going to sample schools with a probability. Okay, that's what PJ is. So every school's got its own probability. In a simple random sample school, in a simple random sample of schools, every school would have the same probability, let's say 0.1. 4,500 schools, sample each school with probability 0.1, you end up with 450 schools, which is roughly the big example. They don't do that. Okay, for some schools, the 0.1 is higher than 0.1. They're really trying to get that school into PISA because it's a grammar school, say. And other schools it's less than 0.1. There are lots of those schools in the country. I don't need to worry about making sure I get all of them into the sample. Okay, so the PJs will be higher than 0.1 in Northern Ireland and Wales. They'll be lower than 0.1. Now, having selected a school, we got it down to I think it's 417 in here. We go, great. These are my 417 schools. Within each school, I don't want all the kids. Okay, I want 40. Okay. The PI bar J is the conditional sign, probability that student I is sampled, given that that school J is in my sample. Given I'm in one of the schools from the 417, what is the probability that I select each child? So within school J, I've got the sampling frame of however many kids there are. Maybe there's 180. Okay. Maybe there's 200, I can't do maths. Maybe there's 200 kids. We want 40. That's a probability of 0.2. Okay. But in another school, which only has 100, and I want 40, it goes to 0.4. So it kind of depends on the school size. Okay. Yeah, if all I was trying to do is take 40 kids from each school. The smaller the finite population of kids in each school, the more likely the kids are going to be in the sample. If the school's got 40 kids, you want 40, well, you want all of them, then these will be 1. So these probabilities are going to vary from school to school to school as a function of school size. And then, so that the top one is the school probability. The next one is what I call the student probability, but it's a conditional probability. Okay. And then here is the overall probability. So the probability that student I in school J is selected is equal to the probability that their school is selected multiplied by the probability that they themselves are selected given that their school was selected. Okay. Okay. So why do I need to know that? Because that's going to lead to 3 different weights, and people only give you 2 of them. So you need to know which one's which. Okay, so those are called sampling probabilities. PISA does not give you those, but that's what's happened when they did the sampling. What they give you are the inverse of those 3 things, which are called the sampling weights. So 1 over the probability that the school is selected is called the school level weight. 1 over this conditional probability is what I call the student level weight. And well, yeah, 1 over the PIJ would give you this one, or you can multiply them 2 weights together. This last one is also what just to be consistent, I should correct my notes and just write, it's just 1 over this as well. Yeah. Okay. So just to kind of keep it grounded in reality, the WG, so the WJ, PISA gives you that, and PISA gives you this. They do not give you that, but we need this for the multi-level analysis. So we're going to have to derive this from the other 2. And we can because they're all related. Yeah. So W underscore J, you can see I've written it here in terms of my notation. That's the school weight. Okay. Wij, that's not the conditional weight. That's the overall weight. This gives you that. But we need to derive a new column, what W subscript I conditional J. That's the one we want. For a 2-level analysis. If all you want to do is a 1-level analysis on students, use this. That's why they give it to you. If all you want to do in the school data set, which only has 417 records, With a school level analysis, you only use that. Because if you want to do a multi-level analysis, you need this and condition one.
So it makes sense that they give you the overall weight because often you do want to use it, but only in single level analysis. Right, okay. So the nice thing is that these weights have substantive interpretations. Okay, so if I go back, so what we say here is that this school, and there are 3 kids, I've only shown you 3 kids from it. Okay, that school represents 19 schools from the UK. So 1 school in the sample is representing 19 from the population. The next school represents 24.6 schools from the population. Yeah. So this obviously had a smaller probability associated with it. So when you do 1 over it, it has a bigger weight. And this one had a higher probability of being sampled. Maybe it's a grammar school. Okay, so it's more likely to be in the sample, and because more of them in the sample, they represent less in the population because they're all in the sample. Okay, so they have a nice interpretation. Likewise here, this is for the students. So this student up here, let's do it down here. This student here, the 6th line, that particular student, that person, they represent 95 kids from the UK at large. Okay, but this one, there's something different about this kid. Oh, the gender's changed. This is the girl, this is the boy. Okay, this student, the girl, okay, represents 81 students from the UK at large. Okay, so you can see within the school, we've got these differential probabilities. Now that sounds odd, because I said within a school, it's just a random sample of 40 kids. But there are these corrections for missing data. Okay, and missing data is different between girls and boys. So I think that's been reflected in these weights. Okay, so they have nice interpretations, so that kind of helps us a bit rather than just being just random numbers that we're just meant to insert in a model. The more understanding we get, the happier we are. Okay. Yes, so I said non-response. I've said this as well. There are some adjustments for that at each level of analysis. Also at the school level, it might be that particular school type, free schools in England might be less inclined to respond, and so we need to have some fix up to the weights. Any questions so far? Right. So let us now look at those weights for the data. So I've renamed the school weight to W2. And I've renamed the overall weight to W. And I've generated a new variable, which I call W1. I mean, use the mathematical notation if you like. I prefer the mathematical notation, but these are the variable names you'll see in Stata or R. Okay. I've generated this conditional weight. Okay, and of course, if I take the school weight and I do 1 over it, I get back to the probability that that school's sampled. Overall weight, 1 over that, I get back to the overall probability that that student was sampled. And this is the conditional probability. So given that the student's school was sampled, what's the probability that a given student was sampled? 0.2. Okay. And so I've now got all 6 things I've been talking about. I've provided with two weights. I could generate a third weight. I could invert all of those and get the 3 probabilities. So we've got the full set of things. Okay. But crucially, this one here, this conditional weight, this is the one we need in the multi-level analysis, these 2. But we weren't provided with this 5.3, we had to derive it, just with probability rules. Okay, so then now having done that, you might, those 6 variables, it's quite good to look at them. Okay, you might do histograms of them. So we've got histograms of the 3 probability variables, school, student, and overall. And then if you invert those 3 variables, you get the weights. School weight, student weight, overall weight. And you can see things like this. Look at this. Here are the school weights. The final distribution, it looks bimodal. That's hinting at stratification. Yeah. They will not always tell you exactly like how they did the stratification. I think I don't know if that's to kind of keep schools anonymous, because maybe that then you don't put too much
information that you could potentially identify what some of those schools were.
Can I say one thing?
Yeah.
I think it's linked to the attainment, the average attainment of
Yeah.
pupils. So that is the
Yeah.
stratifying.
That's also goes in.
Select
It's
the
true.
best, the schools which the highest, have an average highest attainment, and the ones in the middle.
Yeah.
That is the
Yeah, so that also goes in, and school size we'll see as well. Larger schools are more likely to be sampled, so we're going to see that. But yeah. Yes, the national exam results go in. Yes, the school levels is bimodal distribution, then that's hinting at the stratification. Again, you can kind of see kind of things going on here. So it all looks a bit weird. Okay, if you had simple random samples, you wouldn't see that. So that's kind of confirming things that we're suspecting about the data. Now, this is within schools. I've done a random sample of 20 schools, and I've plotted the student level weights. Okay, now we're expecting those to be constant if it really was just a random sample of kids for school. You can see in this histogram, it's a limited number of values because there were very limited non-response adjustments. I think usually for gender and which school you're in. Because if you take a random sample of 15-year-olds, some of them are in year 11, some are in year 10, for example. Yeah, so there's some kind of adjustments for that and gender. That'd be 4. You have more than 4 spikes, 4 spikes, 4. Maybe that's what it is. You like that more. Yeah. Okay. But not much variation. And so that's hinting that we're pretty close to taking a random sample of kids for school. Okay. Apart from these non-response adjustments, perhaps. Right. So there's a lot going on. Here we go. Here's the next thing. If, as I told you, we go back to those weights, these school weights. If the first school represents 19 schools in the population, the second school represents 24 schools in the population, well, if I just add up all of those numbers, I'll get the total number of schools in the UK in the population. That's really good to try and sense check. A lot of what we're doing is not because it's answering research questions, we're just trying to understand the data and be confident that we understand what it's doing and it matches what PISA has done. Okay, so if I add up those numbers across my 417 schools, what do I get? I get there are 4,634 schools in the population. Well, I know there's about 3,300 in England, so that sounds about right to me. It sounds plausible, at least. Okay. Likewise, if I sum up those overall student weights provided by PISA again, this column here, if I add up those numbers, I should get the population of 15-year-olds in the UK. I'm getting up to almost 600,000. Sounds about right. Okay. And with my conditional weights, which is, remember, saying, given the school sampled, how many kids from my school does that one in the sample represent? If I add up those conditional weights, where have they gone? Then I get 145. So it's saying the average secondary school has 145 kids.
145.
Yes, sorry, yeah. Yeah. So I think in England, in state secondary schools in England, it's more like 170. So I'm thinking, well, we've got Wales, Northern Ireland, Scotland. Naively, I'm thinking on average there might be smaller schools, and so yeah, 135. Sounds plausible. Okay, so we're sense checking the data, and if this says a million, I'll be like, hang on, I'm misunderstanding something, and stop. So we're having lots of safety checks to prevent us going further. Now in the actual sample, and this is obviously very easy to observe, 471 schools in the samples, 14,000 students, and the average school size is 29, not 40. Okay, now it's partly because some schools will have less than 40, 15-year-olds, but it's also the non-response. Schools can actually exclude a small percentage of kids as well. There's all kinds of things going on. But it was meant to be 40 and it's 29. Okay. So you can also do histograms of these things. So here's the school size in the sample, and here's the school size in the population, the distribution. And so on. So here we can see there's kind of 40 kids in the sample. What's being shown there, unless
unless that school had less than 40 kids, and then you get the 45 line. The school only had 30 kids, then you get 30 examples. With 20, so you can't be above 45 line. So what this is showing you, it doesn't matter how big your school is. You know, some secondary schools have got 300 kids. Wow, that's super. Like they've got 10 classes, still 40 kids max. Okay. Yeah, and so in a small school, 100% of this is the probability. So in a small school, probability of one of being sampled, obviously it reduces. The bigger the school, the smaller the probability of being sampled because you're maximum at 40. So you can do all kinds of descriptive statistics to try and understand the weights. Obviously very interesting from a kind of a methodological light journal article or PhD is to start doing this like across several countries and then just trying to better understand how different countries do different things and why and how that ultimately affects their results, like kind of case studies. This is just the UK. Okay, another descriptive statistic here. This is the school level probability of being sampled. Okay, and this is school size and the population. So there's 417 dots here, one for each school, which ended up in the sample. Some of those schools at the top, you know, they had a very high probability of being sampled. Okay. And then you look at it, there are two things going on. One is the stratification. This is England. We'll see it on the next slide. This is basically schools in England had a very low probability of being sampled. Why? Because you're oversampling Wales, Scotland, and Northern Ireland. It's massive. So if you ignore the weights, you're skewed massively in favour of Wales, Northern Ireland, and Scotland. So if you're trying to do some UK average statistics, you go horribly wrong. But the other thing is that the larger the school, the more likely it is to be sampled. Okay. We haven't talked about that yet. Why are big schools more likely to be sampled? One reason for that is to compensate for the fact that we've got 40 kids per school. And to get what's called a self-weighting sample. More generally, I don't think that's necessarily done in PISA, but you do see this sometimes. So when you're doing a fixed number of units per group, you need to oversample the bigger groups. And if you did that, you can do what's called a self-weighting sample, which leads, where are we going? Which leads the final probabilities to be a constant value. Okay. And that allows you to not necessarily use weights in a single level analysis. Now, if you look at the final probabilities and the final weights, they're not constant. Okay? So that's not being done here. But that's often done. So yeah, there's a lot going on, right? Stratification. This is probability proportional to size. Certainly stratification by country. Implicit stratification by GCSE results or equivalent exam results. That's going on. Some region and school type stratifications in there as well. Okay. This slide shows the different countries of England at the bottom. We've seen that. Okay. Right, we're getting closer to doing a model, I promise, but it's we also need to be aware of something called effective sample size. So one of the good thing about a weighted analysis is it will hopefully be unbiased. If I ignore the weights, my UK average maths score is going to be skewed towards Scotland, Wales, and Northern Ireland and away from England. Okay, that's biased. I want an unbiased result, so I use weights. But when you use weights, you get bigger standard errors. Okay, a weighted sample is less efficient than a sample of the same size that was a simple random sample. If all you wanted to do was report what is the average maths score in the UK, take a simple random sample. But we don't have that. We have this stratified sample because you want to do the subgroup reporting. But sometimes you want UK average statistics. So it's an inefficient design. How inefficient is the PISA design? My sample of 471 schools, and you can use these formula, okay, on any country. My sample of 471 schools behaves in terms of, for example, estimating the UK mean math score, like a simple random sample of 166 schools. The data contain less information than you might initially conclude. Yeah, 471 schools, it's a big sample. Yeah, but it's because it's weighted, it's inefficient. and it's less informative than an equivalent simple random sample. Now, within schools, okay, I have 20, in PISA, on average, I have 29 kids per school. Okay, what is the effective sample size on average? 29. Why? Because within schools, it's very close to a simple random sample. Yeah, the only time that it's not is because of these small non-response adjustments. So that makes sense. Right? So, within a school, it's almost as good as taking a simple random sample because they basically did take a simple random sample and then just, did some non-adjustments. So it's the school level where you got the really big stratification and oversampling and undersampling of different schools in different countries and so on. Okay. And this is kind of, it's nice to do anyway, but it becomes relevant for some of the weights and choices of different scalings later on. So it's good that we've touched on effective sample size already. Questions? Please, like you said about the implicit stratification on results, just say I'm new to this. Okay, I've been swatting up. Yeah. So when we come to estimate a multi-level model, we're going to use the school weight and the student weight. Both of those will go into the estimating equations. They both go into the likelihood expression, and they're going to upweight and downweight different portions of the data.
It acts as more or fewer cases.
Yeah, it's telling the estimation that these data points should be given more weight, and these ones should be given less weight. It's kind of altering the emphasis rather than giving equal emphasis to all schools. It's upping the emphasis of downing it based on those weights. And if you give more emphasis to England, it will pull the mean back to representative of the UK. I mean, that's very hand-wavy. But.
Can I ask a question about the 2018 sample for Scotland? Has been shown for the first time because they changed the date of collection of data that has a split sample, 50-50, stage 4, stage 5, I think. So you have a group who have already passed the exams, the National 5 exam, and another who are not yet at that stage. So this is 3 is 4. I can't remember now if it says 3 is 4 is 4 is 5. I imagine it's 3 is 4. Anyway. So the weights doesn't really take into account that. Indeed, all the published statistics, Jeremy said, are actually not reliable because they don't take into account at all that there are two. How do we handle that? Is it just that I put a dummy variable to control in my model for these, or can we actually construct some kind of weights?
I don't know. So what I'm kind of what I'm doing here is kind of treating the data as being completely reliable, and as you say, the John Jerome article, which looked at the UK as a whole, but I think had a case study on Scotland in particular. That's really, if you want to analyse the PISA UK data, that's really good to read, very accessible. I mean, I think clearly when you know those things, then obviously you interpret the results differently, and you offer more explanations of things, and then maybe you can do some sensitivity analysis or alter things in the model in light of these things, see how they move around.
Well, you wouldn't construct some kind of weighting for that, because I don't know how would you do that, but it's not something you would solve.
You could, I mean, to the extent to which you observe enough things on your sample, and then you have separate official statistics on the number of schools of different types and all this kind of stuff, you could potentially apply additional weight adjustments yourself. So in a way, you're kind of perhaps you're saying PISA makes some weight adjustments, but it's still biased, and they should have made additional ones. Potentially you could do that because these weight adjustments are just multiplying. When you flip it back to probabilities, you're just multiplying probabilities. So, for example, the non-response ones. You took the sampling weight for sampling schools, and then these are multiplied by a fraction, which is like a proportion of schools who actually responded. And so it's just probability rules. So in theory, you could modify the weights they provide. to give more weight or less weight to, you know, to things which haven't been taken into account. And that would be nice. Yeah, that would be a nice thing to, nice kind of extension to that gerund type work. Yeah, I haven't read the whole thing, maybe did a bit of that, but yeah. Yeah.
Work with survey data, but not using multi-level models because in survey commands to address the experience expectation. And I'm interested by what you said that the weighting increases the standard error. Is that only when you're using weights in the multi-level models, or if, for example, if I have a weighted sample that didn't have cluster memory stratification for it, it's a sample or do the weights then also still increase the standard error?
Don't know.
Okay.
Don't know. I'm not kind of I don't know. I mean, there could be particular designs where you get more precision of that decision. But here, in this setting, this is what's going on. But yeah.
No, I just think I'd always separated the weights when dealing with that kind of data, the weights being the point estimate and then the survey design and the classification being the standard error issue. So it's really interesting to see this kind of.
So this is kind of a model-based approach, and we're going to account for the cluster in the multi-level analysis. The weight's going to deal with the unequal sampling probabilities, but even it doesn't fully account for stratification.
No, that's
because, for example, you sometimes will stratify for a different reason to ensure that a sample looks like the population. It's like better than random, right? You know, if you've got kind of 500 grammar schools and 500 non-grammar schools in the population, in your sample of 100, you want 50-50. You know, you left it the chance, sometimes you get 57, 43, you know. And so you stratify there and say, I want exactly a random sample of 50 grammar schools. And that's almost better than random. And there you don't need any, you wouldn't need any weights at all. But you should tell the analysis that it's been stratified. Yeah. So we're not doing that here.
No,
Yeah.
I think that makes sense.
Yeah.
Thank you. Yeah.
So it's an inexact science is often a comment that people make.
But we're trying to improve upon doing nothing. I think, and so we're trying to move in the right direction and acknowledge the things we still haven't done.
Do you have any more general advice for different complex sample data sets when we're running multi-level model and there's no higher level weights and no way we could calculate the weight?
Yeah.
What would be your approach to that?
Yeah, so if you okay, yes, so if you okay, so what will often happen, I don't have any advice, but just as a comment, I'm new to this stuff. I analyze admin data. There's no weights. This is sensitive. Yeah, often what you would have is only that variable.
Yeah.
Yeah, and if you only have one variable, you can't derive the level specific ones. And so if you use that one, you're implicitly assuming the weight is 1 for every school. So obviously you can do the weighted analysis, the unweighted analysis, describe the differences. I mean, there are authors who do write some things about how to try and recover. You know, if you observe the characteristics of your sample. If there are official statistics saying, you know, my sample, I go, oh, well, that's interesting. I've got 50 grammar schools and 50 non-grammar schools. Well, I know there's 167 grammar schools in the population, and I know there's 3,300 schools in total. I can derive the weight myself. So if you look at the descriptive statistics of your schools, and you can do the same on a population data set, might be another data set, on some, at least the ones in common, off the back of that, you could re-weight, acknowledging that it's, you know, it's the best attempt and trying different variants on that. So yeah, you could try and do things about that. So I'm not, I mean, and the people would have written about this kind of stuff, definitely.
I don't understand the effective sample size for level 2 is around 162.
Yeah.
Where 171. What does that mean in practice?
It just means that your data contain less information than you thought. about trying to estimate UK average statistics. So in my analysis, I'm just going to do sticking gender again. I'm not trying to estimate what the gender gap is in all 4 countries. I'm just doing a kind of a pooled analysis. So, you know, you could enter country dummy variables and then interact everything in your model with them. And that's kind of building the stratification into the model. But that's often a bit overkill. You know, kind of often at most you put in the dummies, not the interaction. So yeah, it's a less powerful analysis than we naively thought. I mean, one way to think about that, if you know, as the weighting gets more and more unequal, okay, that 166 is going to go down, down, down. If effectively there's some schools in your sample which are giving almost no weights, and others which are giving huge, it's like the ones with almost no weight aren't even in the sample. So of course you've got less than 470 schools. There's, you know, half of them are almost not there. So it's just it comes to intuition. So yeah, it has relevance to power. Yeah, not that we do power calculations in this kind of setting, but we often think about power to detect effects. You know, am I going to find like school climate to be a significant variable, or I need lots of schools, but less schools than you've known before. It's less powerful, harder to find effects. That's what it's telling me.
So it's okay, it's still related to have larger standard errors, isn't that? And so I found that in the past that when you weight, you run your model with weights and without some parameters seem to not be significant in the weighted analysis. It's similar, but actually
the point estimates might be similar. If the weights aren't kind of if the weights aren't informative, the point estimates will be similar, but the standard errors still go up, kind of thing. You could get that, Okay, so hopefully this is giving you like a bit more insight. I've learned loads by you. Okay, so this point here saying on average I've got 29 kids per school, and it's equivalent to an effective sample size of 29. Basically, it is basically a simple random sample. That's just doing it for all schools, all 471 schools. The observed sample size, the effective sample size, it's almost always on the 45-degree line, or slightly below in those schools where there was more non-response adjustments. Okay, but effectively, again, that's saying everywhere. It's like we've got simple random samples within schools. Okay, we are ready to fit a model. Okay, but hopefully we're going to go at it with a bit more insight than if we just went, wherever it was. Let's just chuck those 2 variables into the software syntax, not really knowing what they do, which is what a lot of people would do. Okay, so there's our model. It's the same model as before. So regress plausible value 1 math score on gender, get the boy mean, get the girl boy differential, get the between school residual variance, the within school between student residual variance, and so on. You can calculate the PISA. Okay. So yeah, the concern is if you ignore the weights, the regression coefficients are going to be skewed towards Scotland, and especially Wales and Northern Ireland. We need to take the weights into account so that they are representative of the UK average. That's what we want to do. Okay, so here are going to be the first set of results. So I've written here valid approach. Okay, this is a bit too black and white. Okay, so there's I'll call this a default approach, and we can do better than this. Okay, which will be the scaling later on. Okay, so these are the first time I presented these slides, and I'm busy scribbling away corrections for next time I do it. So I would say default approach here. This is the starting position, okay, which is to use WJ and WI conditional J. Okay, so the school weight and the student weight. We're going to specify those when we specify model and state of R. And as soon as you add weights to the likelihood, you shift from maximum likelihood to something called pseudo maximum likelihood. So it's not proper maximum likelihood, which means that the standard errors which are being displayed are no longer the default model-based standard errors. These will be cluster robust standard errors. They're robust to heteroscedasticity, they're robust to arbitrary clustering beyond that specified by the model. Okay, so you might see in the outcomes of robust standard errors.
That's just a small subtlety. It's basically maximum value. Okay, so here are the results. We've got a gender gap of 14, and we've used the weights here. Okay, so this is from using two sets of weights, what we get back, our gender gap, and it's equivalent to about 0.15 of the standard deviation. We'll look at the unweighted analysis next, but we already did that before the break, right? So I think it's around 9, from 9 to 14 by applying the weights. So that's our starting point. Yes, so model 2 is when you ignore the weights entirely. Okay, so ignore the weights entirely. Okay, take the weights into account in the default way. Just use the school weight provided directly, use the student weight which we calculated directly. Not only does that change, look at this, the school variance is much higher in the weighted analysis. Okay, so schools appear much more important than we naively thought. Student variance only goes up very slightly, and so this leads the VPC to go up a lot. There's big differences. So in the weighted analysis, schools, there appear to be much more school inequalities, so school differences, whatever you want to call it, mass achievement. Okay. So we've got bigger gender gap and greater school inequalities. The deviance is much higher because we're putting those weights in, and the weights are much bigger than 1, and that just kind of multiplies up the above line. Okay. So this analysis was biased towards Scotland, Wales, and Northern Ireland in particular. It's more than that because it's more than just country and stratification. Okay, this is treating everything as a simple random sample, which is not. This is taking into account all the probability proportion for size, the stuff in the GCSE results, the implicit stratification, there's explicit stratification for country, school type, and so on. Okay, so the extent to which they differ is because you've oversampled particular things, and that's being ignored here. It's taken into account here. Okay. But maybe, and I'm not, if country was the only thing going on here, and it's not, what I would say was, oh, when we took the weighting into account and we up-weighted England and down-weighted the other 3 countries, the boy mean went up, and the girl mean was say about the same. Okay, suggesting that boys are scoring higher in England than the other countries. But you can't say that there's more going on than just that. Okay, but the more you understand the weights and how they work, the more you can try and make sense of why the results are in the brain. But this is only the default starting approach, I'm afraid. Here's an invalid approach, which is what was asked at the back. What if you only have and in many samples which use 2-stage sampling, they nevertheless only give you the overall weight because they haven't realized you might want to do a 2-level analysis. So if you only have that column, implicitly you're going to have to assume equal weights at level 2. Okay, so in that sense, it's kind of an invalid approach, especially because we know that's not the case in these data. So let's just see what that does. This is going to be model 3. So interestingly, the gender gap, and remember model 1 was the weighted approach. The gender gap looks the same. The boy means dropped a bit, but now the between school variance is much less. And so the VPC is now dropped down. Okay. So we don't really like this model because we know that it's not a simple random sample at the school level. And so what we want to do in absence of that variable is to try and generate it and put it in according to the ways we described. Okay. And we run into convergence difficulties on this model, which is also the red flag. Okay, so I had to stop the estimation at 25 iterations. In Stata, in R, I didn't run into convergence difficulties, and I get the same results in both. So they implement things slightly differently. Okay, so you might also do this, which is, if I had not done any of this discussion, what would we have all have done, including me? I would have specified that as a level 2 weight, and that was a level 1 weight. Okay. And that gives different results again, and these are incorrect. So a lot of people, I suspect, might just do that if they haven't kind of read any of the literature. And that's been model 4. So now my gender gap's up to 17. Yeah. And my school variance is really high, and the VPC has gone up to 0.32. The things are sliding around a lot. Weights matter. Yeah, and how you treat the weights matter. Some of these approaches are just wrong.
There's a default approach, but there are better ways again. There's some scaling things we need to talk about. Right, these Q3, so there's Q1, Q2, Q3, Q4, so we're making some good progress in that. Okay. This was also conversion difficulties. Any questions of this? It's complicated. It's really interesting. It's really interesting actually. But there's a lot going on. This brings us on to doing better than the default approach, which is called weight rescaling. Okay. So, if you're doing a single level analysis, yeah, you would use these weights here. Yeah. Let's say you're doing a single level linear regression, and you did it whatever you want to do. You specify those weights, and that'll be fine. If I multiply those weights by 2, 10, or anything, what changes? Nothing. Only the deviance. Yeah, except that. The deviance changes. Yeah, there's a point estimate thing, standard error thing. So the scaling of weights doesn't matter. The multi-level modeling and scaling matters. The scaling of this does not matter at level 2. The highest level doesn't matter. And if I multiply these by 10, I change the deviance, I don't change anything else. Point estimate, standard error stay the same. But if I multiply my conditional weights, where are they here? The ones actually derived using the multi-level analysis. If I multiply those by 10, deviance changes, but then so does point estimates. Okay. So how the weights are scaled matters. And so that means that various scaling methods have been suggested with no, so here we go, it's not an exact science, different methods are available, different methods will get different answers, it's not clear cut what's best or when you should use what when. So as a minimum, I would suggest applying the 3 scaling methods that I show and hoping for the best, and that they show similar results, and when they show different results, then you're forced to do more reading, try and understand what it is about the data, which is leading to different results, and hopefully that will allow you to steer and say, well, for this particular analysis, these are the weights which we think are most trustworthy. So it's a bit unsatisfying, I appreciate. So what people say is that the student level weights, because that's where the scaling matters, doesn't matter for the school weights, only the student level weights we're caring about, they need to be normalized in some way to make consistent from school to school. Essentially, as you make those weights, those conditional weights higher and higher and higher, if you multiplied it by, by 2, 3, 4, 5, the various components in particular get biased. I think from memory, the school variance goes up and the student variance goes down, and the BBC gets biased upwards. So what people normally do is they try and normalize the weights so that within the school, okay, the weights sum up to the sample size. So if there's 29 kids in the sample, you want the weights to add up to 29. So on average, they're equal to 1 after the normalizing. This is the first method called the size method. These are implemented in Stata as options. So this might sound like really kind of, God, this is complicated. Stata does it as options. I think in R, we'll have to check the Remix thing. So in the code, first of all, I generate the weights using the equations I provide. You do it. And then I show, oh, look, you can get the same results just by switching the options on and off. Okay, but the options are available in Stata. I don't think they're available in R. They're not available in M or Win. So I'll try and show you mechanically what's going on. Okay. And there's a lot of authors listed there to read for advice, starting with Snyders and Bosca, who have got a chapter on survey rates. So they're journal articles which have done simulation studies as well. Okay, so I'm not going to go through in detail here, except to say the first method is called the size method. The level 2 weights aren't changed. The level 1 weights are changed, just rescaled, so they sum up to the sample size. So the school has 29 kids, the rescaled weights will add up to 29. If it has 32, they add up to 32. Okay, that's that method. The second method
is they're going to sum up to the effective sample size. Yeah, but I've already shown you, and this is where we get some insight. Because we've gone through all these laborious steps, I showed you earlier, the effective sample size in each school is almost identical to the school sample size. Therefore, the first two methods are going to give almost identical results, and we understand why. Because the effective sample size is the school size because they did simple random sampling with only these small corrections for missing data. Yeah. So at least we can explain to our audience why those two give similar results. Okay. That's called the effective sample size method. And the third option in the literature and implemented in Stata is this GK method after the two authors, who I should add in here. They do something weird, which looks weird. They just set all the level 1 weights equal to 1. Okay. So even if there'd been some kind of explicit sampling on ethnicity with like white traveller communities oversampled and set all the weights equal to 1. But they changed the level 2 weights. Okay. And they make the level 2 weights equal to the sum of those overall weights. I can't give much insight here. The textbooks, you read the textbooks and things, they tell you different methods. It's like, yeah, but give me the insight, what's going on? Okay, but that's the third method, which is actually to change the level 2 weight and the level 1 weight. So you can use these equations, and we do it in a script file to generate the weights, or you can use the options in Stata. Do these graphs show anything? Okay, these were the student weights before standardizing them. Okay, and these were the student weights after they've been rescaled by the size method. They average at 1. Okay, but it's not a kind of one-to-one translation. It's not that we just kind of divided through by constant or anything like that. There's more going on. Okay, and the same plot for effective sample size is almost identical. It's a bit squished up there at the top because that's almost the same. And here, these are the rescaled student weights by method 1, the size method, and these are the rescaled student weights by method 2, the effective sample size, and they're almost identical. So we're going to see almost identical results. Whereas the GK ones are very different. The GK weights, here are the school weights, the original ones. The y-axis are when the school weights have been replaced by the GK ones. You can see there's a strong correlation of 0.76, but the schools have been moved around, whereas the student weights are now equal to 1 for every single student. They're all different originally on the raw metric, because they've only got a small set of kids per school, and so each kid counts for a lot in the population. They're all set to 1. Okay. Whereas the other methods, they were just on average equal to 1. Okay. So I can describe what I see, but I'm not really giving any insight. I appreciate that, which is frustrating. Yeah. We're now close to fitting refitting the model with so extending the default approach by rescaling the weights. So we've got all this information on schools. We've got these two should be labeled the other way around. This is the N in the population. This is the N in the sample. Apologies. Yeah, you see? So we've got 35 kids in the sample, and they represent 125 in the population. So you need to change those columns. These are the weights in level 2 provided by PISA. These are the conditional weights we derived. So that's our default approach, to use those two variables. In the size method, we drop that one and put in its place the rescaled ones, which on average equal 1. The effective sample size, we use this column, which on average is just under 1 because of the missing data, and you can see they're very similar. So whether we use this or this, we're going to get similar results, but they're going to be different from the default. Because as we know, as you pump up, as you multiply this level 1 weights by 2, 3, 4, 5, 6, remember it, we'll see the school variance goes up, student variance goes down. So we expect the VPC to drop when we go to here. I hope I'm getting this right around. These two will be similar. And then in the GK method, rather than this, you just use this, constant of 1. Well, at the student level, it's going to be pretty similar because they vary a bit around 1. How much do they vary? They don't vary, on average they're 1, they don't vary that much. Most are pretty close to 1. So it's constraining those all to be 1 won't do that much damage. But at level 2, it has changed. And level 2 is where all the actions at. Look at level 2, these are much bigger numbers than they were originally. So we expect these results to be very different. Wow. Okay. So here we go. Let's just do those 3 and then we're done. So here's model 1 was default weights. Model 5 is where we used the rescaling method 1 of the default student weights. What changes? It looks pretty similar, actually. That's this is good. We want to these all 4 look similar. It doesn't matter. We did a robustness check for choice of scaling method. Many of these tests in the literature are results qualitatively similar. Conclusions remain the same. Great. See it in this. Yeah, that's good. That's saved us a lot of effort. So yeah, so 14 or 15 VPC, which was moving around a lot earlier with the dodgy methods. Yeah. Okay. Yeah, deviance is much bigger, but we know that's just because. Yeah, that's not an issue. It's just larger weight numbers. But the point estimates are similar. Standard errors are kind of similar. This one's a bit bigger, but yeah, that's okay. Good. Ooh. Yeah, which means model 6 is going to be similar to model 5. Okay. Can you see?
Yeah.
So what's changing between 5 and 6 are deviance? Changed slightly. Oh, hang on. I went a bit. Yeah, to 1 decimal, not sorry, to no decimal places, we can't see. If you're looking at decimal places, you'd see some small changes. Okay, so that's good. That was as expected. But here's model 7, the GK method. Again, point estimates are similar, but look, my school variance now drops a lot. Student variance goes up slightly, and so my BBC drops a lot. Okay, so again, the GK method relative to size and ESS, and again, what the best method is, relative to those first 2 scaling methods, underestimates the school variance. Okay. But if your research questions are about the regression coefficient, then you still say, oh, but the our central finding about the gender difference is robust. Yeah. So yeah, there's a lot in that session. So yeah, the take-home message is that yeah, all of these data sets are weighted, particularly at the school level. Just ignoring the weights entirely, which was our model 2, gave quite different results for taking weights into account. Okay, so we definitely want to take weights into account. You've got this default approach, which is to use the school weight, which is provided by PISA. Okay, but then we have to derive the student weight as this number divided by that and make a new column. That's the default approach. But you should always then go through each of the rescaling options. Okay, in general, you want to rescale and move away from the default approach. So you really want to pick one of those 3 methods, either the size method, the effective sample size method, which in this particular application are very similar, but often wouldn't be. But here they are, and we understand why, or this GK approach. Okay, so then you'd want to kind of go and look at these journal articles where they talk about, okay, which method is better. The tough call depends on all these different factors. So you want to think about those in the context of the work you're doing, cite some of these authors for their recommendations of when to use which method in which circumstances, and use that to help pick. Should I be doing GK, or should I be doing the size or effective sample size, which are the same? Okay, but in this example, at least in terms of the regression coefficient, as long as you weight how you weight within the set of methods which are appropriate, is okay. Okay. All right.
You need to rest.
So yeah, it's really interesting, but quite hard. Yeah. All right, okay, it's past. The wonderful news is that I don't do any lecturing until 2 o'clock. which is an hour and a half. So obviously we're going to all stop for lunch.
We will have lunch brought in.
Oh, okay. No escape. It's like my. I'll stop the recording now. It's like my desert island. You're marooned on the multi-level modelling desert island. There's no escape, but provisions we dropped by helicopter. Okay. Stop that.